Hello, in this video I'm going to be showing how we can calculate the Lorentz factor gamma using some calculus. Okay, so let's take a look what gamma is by definition. So we got gamma is equal to dt over d tau. Okay, so this is the derivative of our time with respect to proper time. And this is 1 over the square root of 1 minus v over c squared. Okay. Now, we can go ahead and calculate this in a few steps. This shouldn't take too long to do. Okay, so let's take a look at a few things we need to know to go ahead and calculate this. Okay. So we got our d tau squared. That is, by definition, that's the negative of the space-time interval, which is ds squared divided by c squared. Okay. And here, it's a little bit more steps when we don't set the speed of light equal to 1. So you got to be careful. You got to include this factor of c because it's going to show up. Okay. So let's go ahead and see what we get. So if we take the square root of this side, we get that the proper time is equal to 1 over c, and that's going to be, and inside the square root we're going to get the negative of the space-time interval. Okay. And let's take a look at what this space-time interval is, right? So we get ds is going to be equal to ds squared, It's going to be equal to negative c dt squared plus dx squared plus dy squared plus dz squared. And okay, so that's what's going on here under this square root. Okay, so let's go ahead and combine a few of these things. So now we see that our gamma is equal to dt over d tau, and that is equal to dt. And now we got 1 over the speed of light, and we have this quantity under the square root sign. And we have it be multiplied by a negative, so all these are going to switch signs. So we get c dt squared, and I'm just going to go ahead and factor out this minus sign right here. So we're going to get dx squared plus dy squared plus dz squared. Okay, so let's see what we get. So now we get dt, and all this is going to be over 1 over c times c dt, and we have this term under the square root sign, so let's see what we have. So we got 1 minus, okay, so now we have dx over dt squared plus dy over dt squared plus dz over dt squared. And we have all this being divided by c squared. Okay, so now we can go ahead and do a few cancellations right here. We have a dt here, a dt here, and we got a c and a c right here. So this c will cancel this c in the denominator right here. Okay. So now let's go ahead and rearrange what we have. So we got 1 and all this over the square root of 1 minus So let's go ahead and take a look at this. These are what? This is just our velocity squared. So we get the x component of velocity squared plus the y component of velocity squared plus the v component of velocity squared, and we have all this being divided by the speed of light squared. Okay, so let's go ahead and take a little detour real quick. Okay, here we're just talking about the space components of a vector. So let's take a look at this. So say we have a vector v and we dot it into itself. So what are we going to get? And v equals v sub x I hat plus v sub y j hat plus v sub z k hat. So if we go ahead and dot this into itself, we're just gonna get the velocity squared. So we're gonna just end up getting vx squared plus v sub y squared plus v sub z squared. Okay, so we can go ahead and rewrite this term in terms of this. So now we see that this simplifies a bit, and so now this is beginning to look more like what we showed at the beginning. So now we get 1 over the square root of 1 minus v over c squared, which is our gamma, as we want it. Okay, now let's go ahead and take a look at this thing in use. Okay, and gamma pretty much, this Lorentz factor gamma, it pretty much shows up in a lot of places, and it comes right out of the calculus. So let's go ahead and take another look at this to show an example of what I mean. Okay, like we said, let's take a look at, say we got some position vector in space-time. Okay, so it's going to be a four position vector. It's going to have 4 coordinates. Okay, and it's going to be a function of time, and time is going to be a function of proper time. Okay, so what do we get? Well, basically we're going to have our time component, and this is going to be in the time direction, this basis vector. And similarly, we're going to have our x component, and it's going to be in the space, it's going to be in the x, and likewise for the y. And for the z direction, we're going to have a basis in it's going to be in the direction of this basis z. Okay. So now, if we go ahead and we want to find the velocity of this object or this particle, what can we do? We can do dx. Okay. Let's take the velocity with respect to proper time, because we got to show how this gamma factor is going to come out of here. So basically, we're going to get that we're going to get dt. We're going to take the derivative of these coordinates with respect to proper time, but this is going to come out of that. We're going to have to use the chain rule. So let's see what we get. So basically, we're going to get dt by dt, and we're going to get dt by d tau in the basis in the time direction, and similarly, we're going to get dx dt dt d tau, and this is going to be in the direction of the basis in the x direction, and we're going to do the same thing in the y. So we're going to do what? dy dt times dt d tau times our basis in the y direction plus dz dt times dt d tau times our basis in the z direction. Okay. So what do we see here now from what we showed earlier? This term right here is what? Gamma. Here we have another gamma. Another gamma. Here we have another gamma. Okay. So dt, the derivative of t with respect to t, right here, this is just 1. Okay. So now we see that the component in the time direction, that's just gamma. And what do we have here? This is just the x component of our velocity times gamma, so that's just gamma v sub x times our basis in the x direction. And similarly, what do we get? Gamma times our basis, gamma times our y component, the y component of velocity times our basis in the y direction, plus gamma times the z component of velocity in the z direction. Okay. So now if we want to write this a little bit more compact, we can go ahead and put, here we got gamma in the time direction plus, you factor out this gamma. And right here, this is just our velocity right here, this v sub x plus what? V sub y times our basis in the y direction plus v sub z times our basis in the z direction. That's just our velocity. So we can go ahead and write gamma, and this is our time component, plus gamma times what? Our velocity, and this is our space component of velocity. Okay, let's go ahead and take one more look at something. We could show how to use this gamma to show how time dilation, we can show an example of time dilation. Okay. Okay, so let's take a look at an example. Okay, so say we have a period of a pendulum. Okay, and say we're on the surface of the Earth, and let's approximate it to be an inertial frame. Okay, so say we want to measure the period of a pendulum. We're at rest, but we see a pendulum in a moving train. This train's going to be going close to the speed of light. Okay, so let's see what we should measure. Okay, so in this example, we're going to look at the period of a pendulum, and it's to be measured at, say the period of a pendulum is 2 seconds in the rest frame of the pendulum, right? And we're going to take the frame of the pendulum, we're going to take that to be the prime frame. Okay. And okay, so now we want to see what is the period of the pendulum measured by an observer moving at a speed of half the speed of light. Okay. So from the frame of reference of the pendulum, it's at rest, and it's going to see us moving in the opposite direction from. It's going to see us moving away from it at half the speed of light. But since in special relativity there are no special frames, we can equally say that we're at rest and it's the pendulum that's moving. So So let's go ahead and see what we're going to get. Okay, so we're going to say that the proper time of the pendulum, so we're going to have the proper time of the pendulum, that's going to be 2.0 seconds. And since we're calling this the prime frame, we could call this T prime. And since we're talking about periods of pendulum, that's why we're choosing this to be T, the uppercase T. Okay. So, and also the pendulum measures the proper time because it's present at both events, because it's being carried along with the frame. Okay, so let's see what we would get in this example. Okay. And just like the famous saying in special relativity, moving clocks run slow, so we should expect that we're going to observe the period of the pendulum to slow down. Okay, so let's take a look at the equation. We get, okay, so we're going to see that in our frame it's going to be delta t equals gamma delta t prime. Okay, so this is our clock, and this is the clock that we see moving in the prime frame. So as we said, we're going to go ahead and change this to the period we measured. So t is the period we measure, and it's going to be gamma, and this is going to be the proper time. That the clock measures in its rest frame. Okay, so let's see what we get. So say we're moving at half the speed of light. So say if the pendulum is moving at half the speed of light. So we're going to have v equals 0.5 c. Okay, so let's see what we should get. So let's see, we're going to see the pendulum moving out. First, so we're going to see the period of the pendulum. We're going to observe 1 over the square root of 1 minus 0.5 over c squared. Okay, so here we see that these c's cancel, and we have all this being measured by, all this being multiplied by 2.0 seconds, and this was the period of the pendulum in the rest frame. So we should see this to be approximately 2.3 seconds. Okay, now let's take so let's say take another look. So say we observed this to now move at 0.99 times the speed of light. So now we should measure this to be 1 over the square root of 1 minus 0.99 c over c squared. Okay, and here the speed of light cancels. So now we should measure this to be approximately about 14 seconds. Okay, now let's take another look. Say this pendulum was moving at a speed 0.999 times c. Now if you would just plug this in right here and just change this to 0.99, we would measure the period to be approximately about 4.5 times 10 to the 2 seconds, which is about 450 seconds. And if you would convert this to minutes, this is going to be about 7.5 minutes. So here we demonstrated the effects of time dilation and how you could use this gamma factor